This is the lecture for Module 10 in the book Problem-Solving Guide for Electromagnetism and Optics, the refraction of light. This module is about how light gets from place to place, from A to B. So there's A, there's B. Most of the time, light travels in a straight line from A to B. The reason light does this is that it's usually the fastest way to get there. However, the rule is light does not travel the path that takes the shortest distance. It takes the path that requires the least time. Most of the time, it's a straight line. But it's easy to get light to take a crooked path from A to B, or even a curved path from A to B. If B is underwater, light won't travel in a straight line to get there. It doesn't do that. It does this. It refracts like that. It takes a longer distance because the time is shorter. That's the shortest time from A to B. That path is the shortest time from A to B for light. It takes longer for light to get through the water than it does to get through the air. So it takes a shortcut in time, not in distance. This distance is certainly greater than the straight line distance, but the time is shorter. I put takes longer in quotes here because the photons are always traveling at the speed of light. So it's not true that light travels slower in water. The beam takes longer to get here in water because the photons are being absorbed by the electrons. They disappear, they get re-emitted, so there's a delay. But the delay is not because the light is traveling slower. The photons are not traveling slower. It is the beam that's traveling slower because the light particles get absorbed and re-emitted, and there's a delay. So it takes this shortcut. We could also get it to take a curved path. If we dump a 5-pound bag of sugar in a trough of water, there'll be this gradient of optical density. It'll be goopy at the bottom. So you shine a laser in to get from A to B. It'll stay up in the low optical density material and then dip down to minimize the time. And if you want to get cute, what we do is you put a little mirror here. If you put a mirror here, then you can get the light to bounce at B. But it's always traveling the path that takes the least time. A mirage is also the result of light taking a curved path. In a desert or a road on a hot day, the surface of that road or the sand is significantly hotter, which makes the air hotter. Right next to the ground, the air is very hot, which means it has lower density. The colder air up high has high density. So it's a reverse gradient. It's different than the sugar. So the light dips down into the low density layer before coming up to your eye. Light from the sky goes down into this low density layer like this. So here's the light traveling to your eye. Comes down, then it goes up to your eye. When you look ahead in a straight line, you see light coming from the sky. Your experience with light has taught you that light travels in straight lines, and most of the time it does. Your brain is fooled. When you look ahead at the road or the desert and you see the sky, your brain says there's water there reflecting the light. But the light's not being reflected at all from the road. It's just taking a curved path to your eye. And you're completely fooled. So let's look at the refraction. Let's do some calculations. This optical density term is called the index of refraction. And here's some values. Vacuum is defined as 1. There's nothing in the vacuum. There's air, water, glass. Glass has a range. cubic zirconia and diamond will really refract the light. There's one equation in this chapter. It relates the direction of the light in one material to the direction of the light ray in the other material. It's called Snell's law. There's the index of refraction of material 1. That's the direction of travel in material 1. Here's the index of refraction of material 2 and the direction of travel in material 2. That's it. The n's are the indices of refraction. Theta's the direction of travel measured from the normal to the interface between the two materials. If you tend to rush to plug numbers into equations without really understanding what's going on, you're going to make mistakes in this chapter. It's the only equation we have in this whole chapter. When solving problems of this type, it's a big help to draw the normal, a good normal, 90 degrees to the surface. So let's do an example. A light beam enters the water at an angle of 25 degrees above the horizontal. What is the direction of travel in the water? First step, draw a good normal. There it is. Nice, perpendicular to the interface. The angles are measured from the normal. This 25 degrees is not measured from the normal. It's measured from the surface. The angle of travel is 65 degrees. That's theta 1. Measured from the normal. Now we can use Snell's law. We can calculate theta 2. N1 sine theta 1 is N2 sine theta 2. Make sure this is the index of refraction and that is the material. That's the angle of travel in that material. Make sure N1 and theta 1 are the same material. N2, theta 2, the same material. There's the air, 1. There's the angle of travel in the air. There's the index of refraction of the water. That's the angle of travel in the water. We can calculate it, and it's measured from the normal. So it's right here, 43 degrees. So if you want, you can say 47 degrees below the horizontal. The angle of travel of the light in the water is 47 degrees below the horizontal to the right. The refracted beam always comes out on the other side of the normal. Don't put it over here. When the light beam starts in the water, it can be totally internally reflected. Consider a swimmer looking up at the surface of the water in a pool at a low angle. The surface acts as a mirror. What you see when you look up at the surface is a reflection of the bottom. And anybody that's swum laps knows this. You cannot see out of the pool when you're swimming at the surface. The only way to see out of the water is to look at an angle close to the normal, straight out. We can determine this critical angle beyond which light is totally internally reflected by setting the angle in the air to 90 degrees. Remember, it's measured from the normal. So let's do this. Let's take a waterproof laser underwater and shine it up at the surface and see what happens. If we shine it straight up, it goes straight up and it hits the ceiling. We shine it at an angle, it gets refracted, like this. We shine it at a steeper angle, it gets refracted a little bit more. And here, the refracted angle is 90 degrees. It's not 0, it's 90. Remember, we measure from the normal. And if we go further, it'll reflect, it won't refract. It won't come out at all. We can calculate this angle, this critical angle, with Snell's law. So remember, we're starting in the water, 1.33. We're going to call it the critical angle. And we have 1.00 for the air, and the angle of travel in the air is 90 degrees from the normal. So what is that angle? Where is it? Can you find it on the diagram? Well, we first put in the normal, and it's from the normal in the water, right here. That's the critical angle, and it's 48.6 degrees for water in air. Let's do a problem from the text to really get a good understanding of how this works. We're going to use supplemental exercise 10.6 from the textbook. Here it is. You have a laser beam hitting the top of a prism. The index of refraction of the prism is 1.50. At some maximum angle, when it hits this surface, it's totally internally reflected. If I go further, if I make theta max bigger, it will come out this side. We don't want it to come out. What's the maximum angle from the normal? We can hit this top of this prism so it doesn't come out the side. What's that maximum angle? That's the question. So we can't get the direction of travel here because we don't know this angle. But we can draw it. So there's a refracted beam. It's going to get bent toward the normal. It's going from air to glass. Something like this. We don't know what the exact angle is because we don't know theta max yet. In order for the beam to be totally internally reflected at this slanted interface, theta 2 in the air must be along the surface, 90 degrees. So let's draw the normal to the second interface. A good normal, that's 90 degrees. We can draw the refracted beam, which is along the surface because it's hitting at the critical angle. This angle is 90 degrees. We can put that in. Now we can calculate this angle, the incident angle at the slanted surface, theta 1 for the second refraction, using Snell's law. We have the glass, 1.50. Theta 1 is in the glass. 1.00 for the index of refraction of the air, and 90 degrees for the angle of refraction in the air. So theta 1 is 41.8 degrees. We can put that in. 41.8 degrees. Now we have to think, how do we get this angle? If we get this angle, we can calculate theta max. This is the angle we want, theta 2 for the first refraction. We have to do some geometry. There's a number of ways to get this. We know that the interior angles of a triangle add to 180 degrees. There are a few triangles we can pick. Let's pick this one on the upper right. This angle must be 60 because this angle is 60 at the bottom, just from the geometry of the prism. That's 60 degrees. This has to be 60 degrees. We can get this angle because the normal, by definition, is 90 degrees, and we can subtract 90 degrees from 41.8, and we get 48.2, so that's this angle. Now we have two of the three angles that we need. We know that the three angles have to add up to 180. We can subtract 60 and 48.2 from 180 to get this angle. And it's 71.8. So now we have 71.8, and we know that's normal. So if we subtract 71.8 from 90, we can get this angle. And there it is, 18.2 degrees. So now we can calculate that angle with Snell's law. But before we do, demonstrate that there's a whole bunch of different ways to get that angle. In fact, you can use this quadrilateral right here to calculate that angle. But here we're going to start with this 60 degrees at the bottom. If this is 60, that's straight up and down, that has to be 30. If this is 30, that has to be 30. They're vertical angles. If that's 30 and that's 90, that has to be 60. If this is 60, that's a straight line. This has to be 120. Let's put that in. So now we have 120, 41.8, and we have two of the three angles in a triangle right here. So we can get theta 2 by subtracting 120 and 41.8 from 180 degrees, and we get 18.2 again, which is what we got last time, which is good news. So now we can calculate theta max just by using Snell's law. And 1 sine theta 1 is n2 sine theta 2. 18.2 degrees is the angle from the normal in the glass, which has an index of refraction of 1.5. Theta max is in the air. Theta max is 27.9 degrees, and that's the answer. So here are some tips for this module. Draw a big diagram. I've been teaching this class for 20 years, and I've never once walked up to a student and I say, your diagram's too big. Many, many times I say it's too small. There's a lot of things going on, a lot of angles. There's normals, there's beams. You have to differentiate all of that stuff. Use a different color for the beam and the normal. Bring some colored pens so you can follow what's going on. Which one's the normal? I use dashed lines here for the normal and a red line for the beams. Practice, practice, practice. Do a lot of problems. That's the lecture for Module 10.